Dark matter and dark energy are mysterious components of the universe, together accounting for about 95% of its mass energy content. Dark matter, invisible and detectable only through gravity, helps explain galaxy rotation and cluster formation. Dark energy, on the other hand, is thought to be a force causing the universe's expansion to accelerate, a discovery that reshaped cosmology in the late 1990s. According to recent estimates, dark matter accounts for about 27%, while dark energy makes up around 68%, with ordinary matter contributing just 5%. These components are invisible and detectable only through their gravitational effects, making them central to understanding cosmic structure and expansion. In 1884, Lord Kelvin delivered a series of lectures at Johns Hopkins University in Baltimore, known as the Baltimore Lectures. These talks were a deep exploration of physics, including the nature of light, ether, and the structure of the universe. It was during these lectures that Kelvin turned his attention to the dynamics of stars in the Milky Way. He was intrigued by a question that puzzled astronomers of his era: how much mass is really out there in our galaxy? Kelvin's approach was rooted in the physics of motion. He drew on the work of earlier physicists like James Clerk Maxwell, who had explored the velocities of stars, and he applied a method now known as stellar dynamics. Essentially, he looked at how fast stars were moving within the Milky Way and used these velocities to estimate the total mass holding the galaxy together. Kelvin calculated the mass of the Milky Way based on the observed speeds of stars, assuming gravity was the force keeping them in their orbits. He used what's called the velocity dispersion of stars, the range of speeds at which stars move in different directions. By applying Newton's laws of gravity and motion, he estimated the gravitational mass needed to keep these stars from flying apart. This was an early application of what we now call the vecteezy theorem, a principle later refined by Fritz Zwicky in the 1930s. He then compared this to the mass of all the visible stars, the ones we could see shining in the night sky. The numbers didn't add up. The mass inferred from stellar velocities was significantly greater than the mass of the visible stars. In his own words, from a 1901 publication reflecting on his earlier work, he suggested that many of our stars, perhaps a great majority of them, may be dark bodies. His estimate was more of a rough sketch than a detailed map. Plus, he assumed these dark bodies were likely faint stars, dead stars, or other ordinary objects too dim to detect, rather than the exotic, non-baryonic particles we associate with dark matter today. In his 1906 paper, Poincaré calculated the mass of the Milky Way based on the observed speeds of stars and compared it to the mass of the visible stellar population. Just like Kelvin, he found a discrepancy. The gravitational mass was much higher than what the bright, shining stars could account for. But here's where Poincaré made his mark. He explicitly introduced the term matière obscure, or dark matter, to describe this unseen mass. In French, he wrote about the possibility of dark matter contributing to the galaxy's dynamics, suggesting that it could be a significant component of the universe. In 1922, just weeks before his death, Dutch astronomer Jacobus Kapteyn published a landmark paper in the Astrophysical Journal titled First Attempt at a Theory of the Arrangement and Motion of the Sidereal System. Without direct access to observational tools, he relied on data from others, like the photographic plates of southern stars taken by David Gill at the Cape Observatory. Over the years, he meticulously measured the positions and motions of hundreds of thousands of stars, building a model of our galaxy he called the Kapteyn universe. He pictured the Milky Way as a lens-shaped system, with the sun near its center and star density decreasing outward. Kapteyn studied the vertical motions of stars near the galactic plane, how they bob up and down like particles in a cosmic atmosphere. Using a statistical method tied to the vecteezy theorem, he calculated the gravitational mass needed to keep these stars in their orbits. When he compared this to the mass of visible stars, he found a mismatch. In his paper, he wrote, "It is incidentally suggested that when the theory is perfected, it may be possible to determine the amount of dark matter from its gravitational effect." Born in 1889, Lundmark was a rising star in astronomy by the 1920s, known for his work on galaxy distances and even beating Edwin Hubble to the punch on the universe's expansion. But in 1930, at a conference celebrating the 40th anniversary of the German Astronomical Society, Lundmark turned his attention to a puzzle that would tie him to dark matter. Lundmark had been studying the rotation curves of galaxies, how fast stars orbit their galactic centers at different distances. This was years before Vera Rubin's famous work, but the idea was the same: measure stellar velocities to infer mass. In his 1930 publication, On Determination of Distances, Dimensions, Masses, and Densities for the Nearest Non-Galactic Star Systems, Lundmark analyzed several galaxies and compared their gravitational mass, based on rotation speeds, to their luminous mass, or the mass of visible stars. What he found was striking. The universe, he concluded, must contain much more mass than can be observed. Lundmark's calculations suggested that galaxies required far more matter to hold together than what their light revealed. In 1933, Zwicky was studying the Coma cluster, a massive group of over 1,000 galaxies located about 320 million light-years away in the constellation Coma Berenices. At Caltech, armed with data from the Mount Wilson Observatory's 100-inch Hooker telescope, one of the best instruments of its day, Zwicky set out to understand how this cluster held together. Galaxies in clusters don't just float around randomly, their motions are governed by gravity, and Zwicky wanted to figure out how much mass was keeping them in check. Zwicky measured the velocities of galaxies within the Coma cluster using spectroscopy. By analyzing the Doppler shift in their light, how much it stretched or compressed as galaxies moved toward or away from Earth, he could calculate their speeds. Some galaxies were zipping along at over 1,000 kilometers per second, a staggering pace for such a dense cosmic neighborhood. But speed alone wasn't the goal. Zwicky wanted to know what those velocities implied about the cluster's mass. To do this, he turned to a powerful tool from physics, the vecteezy theorem. This principle relates the kinetic energy of moving objects, like the galaxy's velocities, to the gravitational potential energy holding them together. Think of it as balancing a cosmic ledger. The faster the galaxies move, the more mass you need to keep them from flying apart. He compared this gravitational mass to the luminous mass, the mass he could account for by counting the light from visible galaxies and stars in the cluster. The result? A jaw-dropping mismatch. In his 1933 paper, published in the Helvetica Physica Acta and titled The Redshift of Extragalactic Nebulae, Zwicky calculated that the Coma cluster's gravitational mass was about 400 times greater than its luminous mass. In other words, there was far more stuff holding the cluster together than what he could see through the telescope. Zwicky didn't stop at numbers. He named the culprit. He called this unseen mass dunkel Materie, or dark matter, suggesting it was some form of invisible material exerting gravitational pull without emitting or reflecting light. In his paper, he wrote, "If this would be confirmed, we would get the surprising result that dark matter is present in much greater amounts than luminous matter." Zwicky's findings were radical, and not everyone bought them. In the 1930s, most astronomers thought the universe was made of what they could observe: stars, gas, and dust. The idea of a mysterious, invisible substance dominating the cosmos sounded like science fiction. Critics argued his velocity measurements might be off, or that the vecteezy theorem didn't apply perfectly to galaxy clusters. Zwicky, never one to mince words, famously called his doubters spherical bastards, a jab at their closed-mindedness from every angle. But he stood by his work, and history would prove him right. This wasn't Zwicky's only brush with dark matter. In 1937, he expanded his research, teaming up with Walter Bahati to study gravitational lensing, the bending of light by massive objects. Zwicky predicted that dark matter's gravity could lens light from distant galaxies, a phenomenon we now use to map its distribution. In 1939, Babcock published a paper in the Lick Observatory Bulletin titled The Rotation of the Andromeda Nebula. His goal was simple but ambitious: measure how fast stars in Andromeda rotate around its center at different distances, using the galaxy as a cosmic laboratory to test theories of stellar dynamics. Armed with the 36-inch Crossley reflector telescope and a spectrograph, Babcock set out to capture the light from Andromeda's stars and analyze their Doppler shifts. The same techniques Zwicky used, but now applied to a single galaxy rather than a cluster. What he found was surprising. In a typical rotating system, you'd expect speeds to drop as you move farther from the center, following Kepler's laws of motion. Closer objects orbit faster because gravity weakens with distance. But Andromeda didn't behave that way. Babcock's measurements showed that the galaxy's rotation speed stayed high, around 200 kilometers per second, even far out in the spiral arms, where there were fewer visible stars to provide the gravitational pull. In his paper, Babcock reported that the rotational velocity remains nearly constant over a large range of distances from the nucleus. He estimated Andromeda's mass based on this curve and found it was much higher than the mass of its visible stars, about 100 billion solar masses, a figure that dwarfed the luminous matter he could see. Babcock didn't leap to the idea of dark matter right away. Instead, he suggested two possibilities. First, he wondered if interstellar dust or gas might absorb light, hiding some of the galaxy's mass. Second, he speculated that the outer regions could contain extremely numerous faint stars, too dim to detect. Vera Rubin's journey began with a love for the stars, sparked as a child watching the night sky from her bedroom window in Washington, D.C. By the 1960s, she was a seasoned astronomer, but it was her collaboration with Kent Ford at the Carnegie Institution in the 1970s that changed everything. Armed with a new, sensitive spectrograph Ford had built, Rubin set out to study the motions of stars in spiral galaxies, starting with our neighbor, the Andromeda Galaxy, the same one H.W. Babcock had probed in 1939. Rubin's experiment was to measure how fast stars orbit the center of a galaxy at different distances, creating a rotation curve. She used the 2.1-meter telescope at Kitt Peak National Observatory in Arizona, paired with Ford's spectrograph, which could detect faint light from distant stars with unprecedented precision. By analyzing the Doppler shift in the light, blue shifted from stars moving toward us, red shifted from those moving away, Rubin mapped the rotational speeds across entire galaxies. What she found was astonishing. In a typical rotating system, like the solar system, speeds drop as you move farther from the center. Planets like Neptune orbit slower than Mercury because gravity weakens with distance, following Kepler's laws. Rubin expected something similar in galaxies. Stars near the edge should orbit slower than those near the bright, dense core. But that's not what she saw. In Andromeda, and later in dozens of other spiral galaxies, the rotation speed stayed flat, often around 200 to 250 kilometers per second, all the way out to the galaxy's faint outer edges. In her 1970s studies, Rubin measured velocities in galaxies like M31, M33, and NGC 300, plotting speeds against distance from the center. The curves didn't dip, they plateaued. Stars 30,000 light-years out were moving just as fast as those 5,000 light-years in. This defied logic unless something unseen was providing extra gravity to hold them in place. In a 1980 paper with Ford and others published in the Astrophysical Journal, she calculated that the mass needed to explain these speeds was 5 to 10 times greater than the mass of visible stars, gas, and dust combined. Over years, she and her team observed over 60 spiral galaxies, from nearby ones like Andromeda to distant systems millions of light-years away. The pattern held flat rotation curves. By 1978, at a meeting of the American Astronomical Society, she presented her findings, showing plots that left no doubt. Galaxies were surrounded by massive halos of invisible matter. She called it missing mass at first, but soon embraced the term dark matter, echoing Zwicky's Dunkel Materie. Her evidence was ironclad because of her meticulous approach. Unlike Babcock's earlier work, Rubin's spectrograph could resolve individual regions of a galaxy, even faint hydrogen clouds in the outer disks, giving her a detailed picture of stellar and gas motions. She also ruled out alternatives. Interstellar dust couldn't explain it, nor could faint stars alone. In a 1983 paper, she wrote, "The conclusion is inescapable that non-luminous matter exists beyond the optical galaxy." That non-luminous matter? Dark matter, making up about 27% of the universe's mass energy content, as we now estimate.